We're gonna go over the exam. Any impression with the exam? Like any feedback, complaints, things you like, things you hate, question that you hate, in particular.
A little better than the first one.
I see. Yeah. So it should be all graded by the end of the day, and we'll update the Blackboard like usual with the average and like stats. And probably distribution, like per question distribution afterward. Yeah, so let me start with like going over the exam and with the first question in pottery, caching. So which design would you pick? Any quick answer? This one should be really easy. Also why? Yeah.
Or not sector.
Right.
Or
Okay. Pick one. Either sector or not sector.
sector. Yeah, sector.
Why do you want to pick sector cache?
You have less tag overhead and the performance is the same for the workloads you care about.
Yeah, pretty much. All right. What about question B?
Why can't you pick B and say because it's simpler to implement
Yeah.
and has less hardware, so it'll consume less power and has the same overhead with the same workload?
Well, A has less hardware.
Yeah.
Oh, okay. Really, like the sectored one,
So
where you pick the little
It-
segments, the standard knot, instead of just having a block.
so that's one part of the hardware. The tag bit is also another part of the hardware.
Okay.
Yeah, because it actually like save you a lot, like 4 times the tag bits. And whenever you have a tag bit, you have to add comparators, compare the tag bits too. Alright, where's my mouse? So for the next question B, synonym and homonyms. Anyone want to take a stab at this? Yeah.
Page coloring?
You should use a physically indexed hash because it's an L3. So the synonym problem.
For L3, why would you even have this problem?
Yes.
That's a
So yeah, that's the answer. For L3, you shouldn't have this problem. So there's no problem here. So I guess the answer is like, you don't have to worry about this. So your suggestion, don't worry about it.
So would you accept the answer of making it a physically tagged cache? Because I mean, like the only way that you would have this problem is if it's virtually
Yeah.
tagged. So
Right. So that's
you're fixing
more or
the
less
same thing as saying it should
almost the same as, oh, that's not the problem. Yeah.
So on the previous question, it was, that problem was on another exam
Uh-huh.
where the answer was not enough information.
Oh, I guess now owner said that's enough information.
So I'm just a little confused about that.
But I mean, that's the answer because it's L3. There's no problem with it.
At the moment you mentioned that it's L3 and
Yeah.
we have
Right, because earlier level of the cache should have handled that already. So I guess you can like push the design problem to L1, stuff like that. DRAM bit line. Why are the bit line long? Yeah.
because sense amplifiers are big, so you want to amortize that cost over the most rows possible.
Yes. Yeah. So you want more capacity given just the number of sense amp, like the capacity per sense amp. And this is a. Thank you for pointing that out. So, what's the hit rate of this cache?
100% or almost.
Yeah, 100% because there are 2 L's.
Damn it!
I missed it too when I did the solution.
No.
son of a.
You can't. Are you serious?
I'm gonna stab somebody.
That was a cheap one.
It is cheap,
That
yes.
was cheap.
Since you
Can
missed
you-
it.
Can we get full credit if we didn't notice that there were 2 L's there? 'Cause that's kind
As long as you
No, but that's not the correct answer anymore.
Like, wait, if we assume that, like, we missed the 2 L's, just, like, maybe a little bit of credit, like, a little bit. Just a little bit. That's a really, really small mistake. Like, in the scope of the problem, we understand the fact that, like, just one more we miss out of victim cache, all that good stuff. Like it's not that big of a deal, but just missing one L, missing all the points.
Tell that to Onur.
Yes.
Will do.
All you want
Question
to
suggests
right
the
now.
intent of the problems for the answer to that.
Yeah, that's true.
There's no point asking about
Yeah.
what kind.
Why would you ask about the prefetcher and the justification in part 3 if there's no...
perfect. No prefetcher.
Yeah, just don't do anything.
So yeah, so I guess over here you can do Markov prefetcher or don't do anything
Yeah,
because they are fit.
It says minimize cache misreads.
Yeah, because either way, the misread will be the same. Wait, and for the last part, you don't really need anything. And if you kind of miss that out, victim cache is okay as an answer. Yeah.
So is it? So if you put victim cache, it's okay, even if you said that it was 100%.
Because at that point, oh, if you said it's 100%.
I said it's 100%, but it's a weird question to have. Like, am I supposed to not answer the question? Like, that's a weird thing to do.
I would say that answer is okay.
Okay.
Alright, multiprocessor type part 3. Any takers? First one, that should be like
Share.
3 point. Yes, share. The second one,
I said no.
why?
I think I just remember circling now. Probably wrong. I'm being legit. I think I circled no.
I said yes.
Uh-huh.
Because you could theoretically have a system that has a shared memory space, but the memory is distributed.
Yes.
So you would have processor A is just the top bits are 0, 0, and then processor B, the top bits are 0, 1.
Right. I mean, you can have the system that employs this tightly coupled multiprocessor, but they're not sharing anything. So they have fully distributed memory, not sharing.
Well, I mean, they could even share the memory.
They can even
space,
share, yeah.
but if one doesn't access to something that's not in its own space, it
Right.
just goes to the other one.
Right.
Without interrupting that one's process and everything works.
Right. And the third one's, yeah.
Don't they all apply to one?
Yeah, so all of them should be in there, all three, for both of the questions. Because you have to make sure you synchronize all the threads. There's also load imbalance happening everywhere, even though it's a message passing or share cache as a resource contention. So for problem 4, given that, well, you have to take care of all those trees, you have to make sure you take care of that problem for both of them. All right, 5 and 6. Anyone? Yeah, no for both of them. For both types, just circle both.
We only circled one.
I don't think that works. I think.
Why do you need to communicate via message passing?
Because you still. No, it said keep cache consistent. It doesn't mean it's coherency. Like you don't have to employ cache coherence, but you have to make sure it's consistent. You have to make sure it's
What are you
updated.
caching if they don't share a memory space?
I meant even though they have the copy of the data, whenever they sync for each of the threads, you have to make sure the data is consistent across both processors.
No, in a loosely coupled multiprocessor, you're not necessarily sharing any data.
But if you want to pass some data that intentional, like the intentional program to pass out that
Right, but I could
message.
pass that data via interrupts and not have any system of like, I'm going to pass this data into your memory address here or something like that.
But still, you have to make sure that it's consistent. The actual data is consistent.
What I'm saying is there is no consistency problem here. It's a different problem.
Any thoughts? Hi. So they're saying this one for loosely coupled multiprocessor. There's no. Wait. There's no consistency problem. Question 4.
It's talking specifically about cache coherence, and I
Okay.
believe that problem wouldn't exist if you do not share the same
I agree.
address space.
Can't your consistency be maintained by using your message substitutions? So like it doesn't need cache coherence.
But you have to make sure the data sync as something like,
There's
Point
no.
of the send and receive, isn't it? It's synchronized by send and
yeah.
receive. So it's not a cache coherence mechanism that does that.
So I think the point of this question, you have to guarantee that consistency. And if you're unclear about the solution, talk.
I mean, like either way, you're gonna have data shared. Like,
Yeah.
Even if it's not the same address space, you're gonna have.
The actual data that they're being shared between the two processes.
That's not cache coherency. This
No, it's
It is.
consistency.
This,
So
no,
it's
this,
consistency, isn't it?
it
No, it is
specifically
loosely
says
coupled.
a
No,
cache
but the
coherence mechanism.
earlier part of the sentence said cache
Can we
coherence.
define the difference between coherence and consistency? Because I think that'll clear up some of this discussion.
I think the fact
Yeah,
that it's so vague,
The
why
que-
you could answer either way.
The question specifically says a cache coherence mechanism is required.
So
Keep the caches consistent.
why don't I go back during to this
Yeah,
during the
caches
break?
definitely need to be consistent.
I'll go back to this during the break. Okay.
Okay, thank you.
Right. Question F directory.
5 and 6.
Oh yeah. Probably.
Dot. Skip. Okay, yeah, that's one possible solution, which you wouldn't get any points out of that. Anyone that tried this question? Yeah.
199.
Yes. How do you get that?
Did the math.
Pretty much. You did the math. Okay. So how you did the math is
Take the split it up across, split the 32, the 200 megs across all 32, and then like you scale by how many bits you need. So it's n plus 1 bits because you have n processors and one exclusive bit for each cache line.
What if we assumed there wasn't an exclusive bit?
huh?
What if we assumed there wasn't an exclusive bit?
Exclusive. Wait.
Don't you need one?
No, you could use an MSI.
Yeah.
instead of an ESI.
Well, then it's 199 or 200.
If you specifically reason about why you need that extra bit and it makes sense, I'll give that credit. Yeah. So, yeah, how you do it is you convert the 32 gigabyte, which is 2 to the 35 over there, and calculate how much that goes into each of the nodes. So that's 2 to the 35 minus 7 minus 5, which is you get 2 to the 23, which equals to 200 megabytes. So, and this is 8 times 25 times megabyte is 10 to the 20, and that's 10 to the not 10 to the 20, 2 to the 20. My bad. And this means it's 25 times 2 to the 23. And it's byte, you want to convert it to bits, so you multiply by 2 to the 3. So what you get here is the size of each entry in the overhead for the directory is 2 to the 3, which is 8 times 25 equals that size, which means that you need 200 bits. And you need 1 bit for the presence bit. So that means you have 199 number of cores. All right. Going on to question 2. Varun, do you want to do this question?
Yeah, I guess.
Do you want to tell what's the most common mistake that people got? Because you were sad. We all sad about that.
Yeah, a lot of you almost got this question right, but didn't.
All right.
So-
Take the mic.
Yeah, okay. Oh, there's an actual mic.
Yes.
Ah.
I can carry it.
So just look here. Yeah. Okay, so this question's about cache coherence, which it became apparent that some of you guys don't know what cache coherence is, or you don't know the messy protocol, either one. So you're given like all these initial states for caches, and then there are 5 memory addresses in between. So anyone who thinks they got this right, want to explain how they went about doing this? Go for it.
I mean, I can't do the whole thing right now, but essentially the way that I approach it is through what procedures can I make the things at the top look like the things at the bottom? So you can look at which addresses change and then which things go from exclusive to shared or from invalidated to modified or exclusive.
Yeah, that's essentially it. I can actually quickly just run through how I would go solving this. Important things you should know about like the messy protocol. Whenever you do a write, you insert the block with the M tag because it's been modified. A lot of you made the mistake thinking a write could end up being an exclusive. Exclusive just means you did a read and it's the only one that owned it, so it can be promoted up to modify without causing any like signal to write back or anything like that. Yeah, everything else is. The most common mistake on this was the fact that, so since these are all, this is a direct map, right? Yeah, cache. The set it's in actually matters. So the biggest mistake everyone made is instead of putting the address here, they excluded the bottom 2 bits and just put the tag, which was really unfortunate. Huh? Well, the rest of the address is the set bits, which you have to figure out. So, you know, like you have your tag bits, your index bits, and your block offset, and we gave you enough info to figure that out. And I'll tell you what the answers are as I guess I walk through it. Is there a way for me to show the answer one on the board?
Yeah, why not?
Oh, just drag it. I don't know where my mouse is. Oh, here it is. So.
You're given that the block offset is 6 bits, and then there's 4 sets, so that's 2 bits.
So the answers are here, and I'll explain how you'd go about doing it. So like.
Why don't you work it on the board?
Okay, fine. I'll move it away. No answers for you guys. Okay, so the way to do it is the first clue I give is like in cache 3, you're pretty clearly like nothing is, it's a cold cache at this point. Everything's invalid and nothing's done. And you can see that there have been 2 changes basically because there's a modified and a shared. And if you go look down here, there are 2 changes in cache 3. So clearly those 2 have to happen at one of those, at either the first or the third instruction. And one of them has an eviction, the other one has a write back. So what you have to find is which one would have a possible write back, and that was, or which one would have an eviction. And that's pretty clearly the write, because everything else that used to be there was shared, and now they're all invalid. So those are the evictions. And since the other one doesn't cause an eviction, you know your first instruction. So that means it's going to be set 0 of cache 3 with the address with the tag. So you have for your tag for the first one, and then it's in set 0, so you know your top 2 bits are going to be 0, and the offset for all of them was 0, which was stated in the question. So that's your address. And then since it's in the modified state, you know it was a write. And since the shared states were in all the other caches except for cache 3, all of them have to be evicted, because when you have modified, it has to be the only one owning that. So then you know that it was evicted from all of these caches. And that's how you fill in the first line. And then you go to the third line because it's easier. And you know it's pretty clearly going to be that address, which is And then you want to figure out the set bits, and since it's the third set, you're gonna have, what's 110? That's C, yeah. C0, and since it's in the shared state, that means it can't be right. And since it didn't cause an eviction, you don't fill anything out here. Then for the second one, you know what's changed in cache 1 that can't really be explained by like another cache change. And that is, let me see if I can just go up and see the initial state. Where is the mouse? Oh, this is great. That one was 32FF80, so that's the third one. And so yeah, so you basically see that the only one, certain things were invalidated in the first cache, but that doesn't really matter to us because when you add something, when we have a request served by the cache, it's not going to invalidate it. So you have to look for the one that changed that wasn't to an invalid state. So that's the address. That's the one in the second set, which can be 32FF80. And then because it's again in the shared state, not the modified, it's a read. And it didn't cause an eviction, so you don't need to do anything there. And I think that one might cause a write back. Did that one cause a write back? Because it was 32FF. Yeah, and that one, and you also know this one caused a write back because there's a 32FF that in this cache, and it gets downgraded to shared because it was in the modified state earlier, so you need to write back to the earlier things. Well, we're 4 and 5. 4 and 5, you have requests served. They're both served by the 0 cache, and one's a write and the other one's not a write, which you can figure out by the fact that one caused an eviction. And so the two changes are pretty clearly going to be in, I think they're, yeah, in the first set and the third set, which were both invalid and now aren't invalid. It's like pretty self-explanatory for write back now for eviction. Yeah, so from there you just know that the next one was caused an eviction, and so that's going to be the one that's going to change the, which one caused the eviction? That was that's going to be the 300 add-in because it's in a modified state, meaning the other one that was in an exclusive state is going to get kicked out of the first cache. This is going to be 30040, right, and then this caused an eviction in the first cache. And then that just leaves the last one that changed, which is going to be because it didn't cause any evictions or anything else, and it was just ended up in the exclusive state. Do all of you get how this worked? Any questions?
Did we actually need the write back column to do any of this?
Right back. I don't really think so.
Because I ended up just ignoring it. I wasn't sure if that was.
I'm not sure if when I was originally writing it to make the order proper, you did need it, but then we added in the request served by cache to like make sure the order was certain. So I'm not sure if you needed it after that.
And
Did
so
we,
I guess
yeah.
that brings you to another question, just write back in general. This is a write back cache.
Yeah.
What does that mean? What does it mean for a request to cause a write back?
Write back just basically means instead of when you make a change to a block in the cache, it doesn't automatically get reflected in the latest part of the memory system. So your coherence protocol has to keep track of basically which blocks are dirty.
And then what
So
does it mean for something to cause a write back?
yeah, so causing a write back means there are basically two ways you can there are two ways you can cause a write back. You have to evict a block that's been modified, and anytime that happens, that's going to cause a write back. Or instead of evicting one, you want to access that same block, and that'll like downgrade it to shared if it's not a write, if it's a read. So if you have, let's say I want to like read from this block now. That would let's say I want it in cache 2. That would move this to an S and an S, and it would cause a write back because that modified state needs to get reflected in the system.
Okay, but something that doesn't cause an eviction.
That doesn't cause an eviction. If I had
A read, wait, well, isn't
a read in a different cache, of the same tag,
okay.
because you need to reflect that change, and the only way to keep track of that is
So
to
if you read from in cache 2, okay, I understand. So you need to have that thing from cache 3 written back.
Yep. Yep.
How is it possible that in the initial state there are 3 exclusive states for the same cache block? Cache 0, 1, and
Not the same.
They're not the same block. They're in different sets.
They're in different sets. That means it's a different address. Yeah. Anything else? Cool.
All right, so what's the next one? I think it's TLD RAM. Yeah. So why is the near segment faster? Lower latency. Why? Yeah.
Because it has a shorter bit line, so that it's less capacitance and it lowers the.
Yes. So because of the isolation transistor disconnects, pretty much you shorten the bit line through that disconnection. So the capacitance is lower. That's why you can. That's why the latency is lower. How about the 4 segment? Why is the access latency more than the commodity RAM?
The isolation transistor adds resistance.
Yes. Alright, so given this setup where the 4 segment is 960 rows and the total DRAM has 1024 rows, what's the capacity loss if you use it as the cache, write back inclusive cache?
It's just 64 over 1024.
Yes. What about D?
1024 minus.
No, yeah, that's correct. What about this? If you use not MIU as a replacement policy, what's the minimum number of tag bits required?
Could we assume that the near segments are 64?
Oh, for this question? Yeah, it's inferred from that setup that is 64 rows. Anyone want to try or? Okay, first, how many tag bits do you need for this particular question? Yeah. Log, and then it's the upper limit. Yeah, so it should be 10. Yep.
Times the number of things in your cache, which is 64.
Yes. So that is the number of total tag bits. And then what else you need if you want to use this as an inclusive cache with not MIU as a replacement policy?
You need to remember which row in your cache is the most recently used, and since there's 64, that's 6 bits.
Yes. So in total, you don't really need MIU bits or anything inside each of the rows, but because there are only 64 of them, you can just use 6 bits to remember where's a MIU location. And what else?
Valid bits.
Yes. Actually, there are 2 ways you can think about it. You can add a valid bit. You can just use the valid bit as early access in the DRAM row, I think. So I'll take both ways of approach as a valid answer. So yeah, you need a valid bit, so that adds to this. What else?
The dirty bit.
Yes, you need a dirty bit. And do you need anything else?
Oh crap! You do actually need a dirty bit, don't you?
Yes, you do need a dirty bit.
Well, I was thinking because you don't need a valid bit because you could just make it an invalid address.
Yeah.
So you would know. But
Yeah,
you
I remember what you said
Yeah.
there. Yeah.
Damn it.
All right. So anything else that do we need? Yeah, that's all. We take care of the valid bit. We take care of whether it's dirty or not because it's a write back inclusive cache, and take care of the replacement policy. So that means that that's the total size, 12 times 64 plus 6, and I believe that's 74 bits. And here.
That's how I feel about this exam.
Yeah. And I had all the work to show that though.
Yeah. So I mean,
Wait, no, we don't need these bits, but we actually.
yes.
I'm assuming there's pretty much no partial credit on any of these questions.
Actually, for the question, I think what I get is like if you figure this out, you get some partial credit. If you figure this out, some credit. There's some credit and also this. But then I got our combination of hit and miss. So yeah, that's some partial credit for each of the things that you got right in the show your work part. Alright, so for question E, if you use it as an exclusive cache, what's the capacity loss? Come on, you guys got it almost correctly. Almost of you guys got it correctly. Yes, it's 0. You don't lose anything. And what's the tag source size? The same as question D in this case.
Because of your placement policy, you actually need to have a tag for every row.
You need to have a tag for every row inside the near segment.
You need it for the
No,
first segment too.
you do need it for the far segment because when you replace a row,
Uh-huh.
you can put it back in any of the locations.
It says you just swap them.
It's-
No, you're just talking about the tag bits.
Yes, the tag.
The tag bit that needs it for every row, yes.
Yes.
So you have 24 rows and 10 tag bits. And what else do you need? Yeah. You don't need the dirty bit.
And you also don't need balance.
You also don't need a valid bit. But you need one more thing to pick which one you want to evict from the near segment.
You need a 6-bit.
Yes. You need the 6 bits. Right. So in total you need 10,200 bits. Alright. Oh shit. And for this question, this one is actually most people got it right. Now assuming that we change where the isolation transistors, yeah.
You need one row so that you can copy stuff over.
You have a row buffer for that. So
And why didn't mention that in the paper? That they needed one to use up more rows. If we have a row buffer. I remember reading that in the paper and it's like, why can't you use the row buffer?
why can't you use the buffer? But just for the transfer, unless the row buffer is open and used, right? Because you can always just close the row buffer.
Yes, if you're swapping two things,
Uh-huh.
having one row buffer is sufficient.
Yes, because you're swapping just one row in the subarray. You can just use the row buffer, activate. You don't have to read and pre-charge it back to the other row.
So I think you're not thinking about TLDRAM.
It might be the row.
You're talking about what's the copy?
Row clone. Yeah.
Because in row clone, you use up one row buffer to just store all zeros, so that you can just copy zeros into any of the other rows on the thing.
I don't think that's what.
All right. So for question G, any takers? near segment access latency when you increase the
You're gonna have higher latency.
you have higher latency. I think everyone got this correctly. And for far segment. Yeah.
Lower latency.
No, because now you move where what you did.
You increase the ones in the near segment, which
Yes.
means you have fewer in the far segment.
You have fewer in the far segment, but what you do is you just move the isolation transistor. Think about when you connect everything, the bit line length is the same.
Oh, I see what you're saying.
So that's why it stays roughly the same. How about near segment access energy? Yes. For segment access energy,
The same.
yes, it's the same. Hit
We
rate.
get points for getting it right now.
Huh? Oh, right now? Sadly, no. How about hit rate in the near segment? Up, yes. All right, multi-threading. With that particular setup, how many bits are used for tag index and byte in blocks? This one should be really, really, really easy. Right. Let's start with the byte in blocks. What's the size of the cache line is, I think 16 bytes.
So the index was 3.
Index was 3.
And the byte block is 4.
Yes.
And then the other one is 16 minus.
Yes. Does anyone know how to get all those bits? Yeah.
I know how to get to the byte block was, you know the cache line is 16 bytes.
Uh-huh.
So that's the amount of data that's stored. So you know that log base 2 of that is like your byte block.
Yeah, it's 4.
So yeah, that was 4.
Yes.
Uh,
For the, do you know how to get the set bits? I mean, I can explain how to get a set bit. Okay. Oh,
I also
you
don't
did.
have my glasses on, so I can't see the question.
I that I cannot tell. So byte and block 4 bits, right? And then the set bit is 3 bits, and then the tags is 9. If you given this configuration, look at the access pattern. I think most people got them correctly, which is if you run thread 1 followed by thread 2, I think we make it such that the byte in block is just the last number, and set bit is this. And A and 2 pretty much map to the same set because it's 2 or 8 plus 2, which is the same set. And the rest are the tag bit. So if you access this, followed by this, followed by all of this, you get miss, miss, hit, 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 hit. Right. So for thread 1, you get hit, hit, and then 6 misses. And then,
It's miss.
my bad. Yes, miss, miss, and then 6 hits. And thread 2, you get, what do you get for this? Yes, miss.
Miss. Hit.
Uh-huh, uh-huh. Yes,
Miss.
yes,
Miss. Hit.
yes. So you get 2 miss, 2 hit, 2 miss, and 2 hit. That's what you need to work on part B. Yes, part B. Because now, assuming processor 1 execute thread 1 followed by thread 2, so the execution time, and this depends on how you assume how each of the threads starts. You can, some of you might think, oh, thread 1 and thread 2 start at the same time, so thread 2 has to wait.
What? It says that it starts with thread 1.
Yeah. But what if they have been running something else before us, and then you run to this part? I'm just telling I accept several answers.
Oh, okay.
Yeah. So if you had the assumption, it means that the total time would be the execution time of thread 2. That I accept that answer too. Plus context switch time. Either that or you answer how much thread 1 spent. And then after thread 1 is done, you start executing thread 2 and how much time does it spend. So in the first case, you have 2 misses, and this will be 55 cycle-ish, right? That's stated earlier. And then this, I believe, is 5 cycle each. So what you get is, what is here? 5 cycles? Yeah. And then you have 20 20 times 7 add instruction in between. So what you have is 110 plus, that's 30 plus 140, and that adds up to 280. And then you context switch. So if you do the approach where you assume thread 2 start whenever thread 1 start, you have to add 10 to that. That's also the total time. So the total time right now would be 280 plus 10 plus the time you spend running this. So you have 2 miss, 2 miss, 2 hit to hit. That means you have 55 times 4 plus 4 times 5 plus 140. And that adds up to 380. So the total time would be this plus 380. And that's 670. Right, everyone got that part? Okay. Oh. Right. So for part C, what if it is fine-grained multithreading? If you look at the program, now if it's fine-grained multithreading, what's going to do is execute this, followed by this, and this. And that, when you do this, and this, and this, and this, it causes eviction. So what happens, every cache access becomes a mess. So now with F, G, M, T, all cache access miss. So if you want to calculate the execution time for thread 1 and 2, you can just calculate by the number of total cache access time, the time you spend accessing the cache, plus the time you spend executing these 20 add instructions. So what you would get here is, because all 8 of them are misses, and you start with thread 1 followed by thread 2, coming back to thread 1. The easiest way to do this is to figure out what's the total execution time for both of the 2 threads, which would be, you have 8 cache accesses, so that's 8 times 55 plus 20 times 14. And that sums up to, no, actually there's 16. You have 16 cache accesses, my bad. And that sums it up to 1160 cycle. And because thread 1 finished before this last memory accesses, so what you would get for thread 1 is just subtract 55 cycles from this. So thread 1 execute done by 1105 cycle. And for thread 2, the most accurate answer, if you assume a thread 2 start whenever this instruction starts, you have to subtract 1 from this, which is 1159 cycle. But I don't think anyone answered that, so 1160 is okay. Right? Now for the evil part, the switch on events. So if you actually trace to the execution timeline, it will repeat. So let's look at this memory stream and see what's happening. Oh, I'm gonna move this up a little bit. So all these cache accesses are misses. So the first 5 you're running thread 1 and thread 2, and it's like time spent for each of the action. First 5 cycle, you figure out, oh, this is a cache miss. And then at 15th cycle, you context switch to thread 2. And then you spend 5 cycle. So you spend actually 10 cycle over here. And this is a cache miss. And because both of them are cache misses, what you do is you context switch back to thread 1 and wait. So that's 10 more cycle. And this is 30 cycles, so you wait. You wait 25 more cycles because the total from the point you figure out is a cache miss. You have to wait 50 cycles, and that's 25. So you wait 25 more to resolve the cache miss. And then afterward, you spend 20 cycles doing add instruction, 5 more cycles to get the second cache miss. This is the first miss. 10 cycles to context switch back to thread 2, and by this time, thread 2 cache miss is already done. Right? So at this point, 0 cycle to resolve the first cache miss, and then 20 more cycle over here to do the 20 adds. And once that is done, 5 cycle to figure is a second cache miss. And then 10 cycle to switch it back. And then once you switch back over here, there's 30 cycle, 35, 45 cycles. You spend 5 cycles to resolve the second cache miss. So the second cache miss here is done. And then once that's done, 20 more cycles to do the add. Afterward, 10 cycles to do the context switch. No, actually it is. Once you do the add, 5 more cycles to figure out that you have the third cache miss. And then 10 cycles to context switch back here. And as you can see, it starts repeating, right? So you can actually stop at, where did it stop? Over here. So this is 75 cycle. And then after you finish this 20 adds over here, this will repeat. This whole pattern will repeat over and over. And this is 35, 40, 50, 60, 70, 75 cycles total. So at the beginning you have 75 cycles. And over here you have 75 cycles in repeat, right? So let me clear up this. So you have the initial 75 cycles plus 75 cycles that would repeat this pattern 5 times until it resolves to that location, which is right before everything ends. And that's where you just finish doing the 20 add instructions on that last 20 adds. What happened afterward, you spend 5 more cycles to resolve the last cache miss, the 8 miss. 10 cycle to context switch. And then at that point, the 7th miss is done. So it's 0 cycle to resolve the 7th miss. 20 cycles to do the last batch of adds. And then 5 more cycles to resolve the 8th miss. 10 more cycles, context switch back here. At this point, 10, 30, 35, 45, 5 cycles to resolve this 8th miss. And now you're done with thread 1. And what's happening afterward? 10 cycle, context switch back here. And now you already spent 25, so you do 25 more to finish running 2 threads. So we finish over here. So that's 15, 35, 40, 50, 55, 65, and that's plus 90. So if you add everything up, you get 615 cycle. And this is where thread 1 is done. So for thread 1, you subtract 35 from this. So you get 115 minus 35, which is 580. That's it.
Could you go to the question again?
Oh, okay. Yeah.
Oh, okay.
All right. So yeah, if you guys are approaching this question in some weird way and you think you do it partially correctly, talk to me or talk to us. Because it's hard to just look at what you draw in the timeline and try to figure out what's going on, especially when you're rushing this question toward the end. Because I see that happen to some of you guys. What's the next question? All right, tracing the cache. Xiaobo, want to do this? Are you still repeating the pattern in your head? The pattern that you posted on Facebook.
Oh yeah, I still know the pattern. So like that. Right, magical devices. So actually from grading this question, I can already memorize the pattern of each answer, which is very sad because they're just random strings of letters. Anyways, anyone want to take a stab at how to work out this question? Sure.
Well, the easiest way to find things. Okay, I guess the first step that makes the solution easier to find is working out how many spots there are.
Definitely.
And what relations of memory would evict what, since you know everything's contiguous block.
Definitely. So what does contiguous block tell you for this question?
For example, I think there was like 4 sets with like 2 things in each. So like there's 8 letters, so you know that like there has to be 2 in each.
That's correct. Do everyone follow that? So then the next question will be, how can we use the given information to figure out what to do? So for example, for the first processor, the 6808D, we know it's a direct map. So there are exactly 2 cache lines in each set. So how can we use the miss trace to figure out which one is in which? Yes?
See which ones cause the other one to be affected. So they're together.
All right. So let's just walk through it a little bit to see more or less how we can go through it. For example, you see A is missed, which is a compulsory miss. Then B misses, but then A misses again immediately. And from the trace, we know that these 3 are actually next to each other. So for example, this tells us right away that A and B are in the same cache line. Now we can actually just forget about this not cache line, same set. Now we can just forget about this too for the rest of the question and try to figure out the other 6. So if you keep walking down, you realize like H, B, G, and then E. Now we have 4 new information without any extra information, so we can't really figure out anything so far. But if we keep going, eventually you see this pattern again, the CGC pattern. So we know that this guy, compulsory miss, now it's in cache, G misses, now it's in cache, and then immediately C misses again. So this tells us that C was evicted by the last coming cache line. So that puts C and G in the same cache line. in the same set. Then with this information, if you backtrace it, you can start eliminating the choices. And for example, you know these two are the same, then H, and then there's a D here. And the next, we know B doesn't matter. So you actually have D, H, these guys don't matter, and then D. So D and H are in the same set. And this leaves you only with E and F to be in the same set. And then you have the layout of the entire memory. Was that clear?
Yes.
All right. Then you go to the next question. The next question is really just, wait, wrong PDF file. Wait a second. There we go. Now if you go to the next part, the next part is really just making you simulate this small cache by hand. And as long as you have enough time, I think it's really easy to do. Did anyone have trouble with this one? And in particular, this is the fully associative cache. And the reason why I made you do this one first is because you actually don't need the previous information to solve it, just so you can get some free points before diving into the more complicated part. Now, this is the process that actually is more interesting, the two-way associative. From the first question, we know that two cache lines are in the same set in the direct map. In the two-way associative, there are 4 cache lines in each set. So if we say number the previous sets 0, 1, 2, and 3, then in this case, the even sets become the same set, and then the odd sets becomes the same set. Is that clear? Then using that information, how you go about to find out which 2 sets merge? Any? Yes.
Well, the easiest way to figure out which 2 merged.
Mm-hmm.
You know that A and B are already there.
Mm-hmm.
And you know that what was H with D, I think. H was with D,
Mm-hmm.
G was with F,
Mm-hmm.
and G was with C.
Mm-hmm.
So if those are your order of misses, you can go back into the other sequence.
Mm-hmm.
Actually, I think this is on my scratch. Paper. Let's do it right here.
Can you at least give us? Oh, there you go.
So from there, you can work out that. I can't remember this. I can't remember how I worked out which 2 were.
All right.
Which 2 exactly were paired up, but modeling it after that was easy.
Okay. Well, so then if you look at the first 2, we already know that A and B were in the same set from the direct map. And if they're in the same set from the direct map, they have to be in the same set for two-way associative. So then we know that A and B already fill up the 2 spots for this particular set. Now, if there's any other cache line that goes into the same set, it's going to immediately evict A and B. Now, the trick here is that now you have 2 more requests that miss. And then if you look up in the previous part, you know that until you get the first E request, there's actually a whole bunch of B's and A's coming in here. So this means that none of the other 2 requests down here, H or G, cause an eviction of A and B. This means that both H and G ended up in a different cache set. Now, H and D are in the same set originally, and H and G and C were in the same set originally, as you recall. This means that those 4 cache lines end up in the same set. So this leaves you eventually with E and F being the same set as A and B. So sort of like a small math logic deduction there. Did anyone follow that? All right. And then with that information, you can fill out who is doing which, and you can use that to simulate the final cache. And then how you do the last question? Count the misses. Yep, that's it.
And you divide by the total.
By a total, yes. So
What's the numbers?
I think it was 17, 16, 19. The two-way associative was actually the minimum, which is Well, it was an engineered question, but you can sort of imagine why the middle ground it normally performs better than the other two in terms of total misses. All right.
Well, I mean, so it's intuitive that a highly associative cache would perform better, but in
Yes.
this case, it turned out that you were getting so many evictions that.
Correct. It's because of how the trays were designed. So again, it's a highly engineered question. It doesn't necessarily represent real life workload. All right. Next question. Paraj. Want to take over? You can take over. Come on. I'll do the next one.
Memory request scheduling. So the first question asked is, for each of these applications A, B, and C, what's their latency using FR-CFS? Anyone had any question about using FR-CFS on this? Yeah, it's pretty simple. So first of all, you have to check between these two different channels. You have to take the maximum value because that's the time when each application is done. So if you look at, where's the marker? Oh, here. If you look at application A, in channel 0, you have to run until this particular request, like the last request, is being serviced. And if you work it out, you'll see that there are 8 hits and 3 misses for channel 1. Channel 0. And this is channel 1. For channel 1, is done roughly around that point. So if you calculate, work it out, you see that you have to, so you issue this first, that's a hit, and then the next request is R4, so there's 1 miss, and then 1, 2 more hits. So it's 3 hit plus 1 miss. And the maximum of this 2 is this one. So the latency of application A is equal to 8 hits plus 3 misses, and you just multiply the number of accurate pre-charge and read and write. For application B, in channel 0, so even though, so if you can just look at number of total requests over here, which is 12, and you see that if you do the 8 hits, if you actually do the work for application A, which got 8 hits, 3 miss, the last request that haven't been served is this one. So you add 1 more miss to that. You get 8 hits and then 4 misses. For channel 1, you get that the number of hits and misses would be, you have to include the one from application A too, and until you recharge every request from application B, and you get 7 hits and 5 misses, which is pretty much all the requests in that channel. So this greater, so the total latency would be 7 hits plus 3 misses. For application C, because it's only exists in channel 1, bank 0, actually this exists in both cases. Over there in the top channel, you spend in total 7 hits and 3 misses until it gets service. For channel 1, it's actually 7 hits and 4 misses. And this is greater, so the total latency would be 7 hits plus 4 misses. Anyone has any question with this? Right. So for the next question, it asks a new policy where you batch requests by n. For example, if you said n is 3, then you look at the first 3 requests first, and then do f of CFS within that batch, and then you go to the next batch, and then next batch. How might this improve performance for application C? Any, yeah.
Well, sometimes application C, because it doesn't hit the row that the other applications have, it gets kind of pushed off to the end.
Yes.
So if you have a sufficiently small batch size,
Yes.
you can prevent it from being carried off by the row thing.
Yes, exactly. So application is not memory, and the memory intensity of application is not that intensive. So you don't have to wait for younger row hits from memory intensive application to be fulfilled. How about the, so that means it gives better fairness for application, all of the 3 applications compared to FR CFS. What was the downside of this policy? Yeah.
It doesn't maximally exploit row buffer hits.
Yes. So that actually lowers the RAM throughput, lower number of row buffer hits. So now, assuming that you run this batching policy, and then you get the number where application A has 4 row hits, 8 row misses, 4 hits and 8 misses. Application B, you get 3 hits, 9 misses. And for C, you get how many? 2 row hits and 5 misses. How would you work on this? Anyone want to take a stab at this? Yeah.
Oh, when I did it, I kind of just looked at channel. I looked at channel 0 first, and like I don't know, the numbers just kind of were working out. Like I tried just looking at different numbers.
Sure.
Then when I looked at channel 1, I saw that the number of different rows that were accessed was if you looked at like if you wanted to include the only request from C.
Yes.
In first access, and you could, if you had 7 or 8, then you can include C, and you would have 5 different rows. Is that way you could have 5 hits and then possibly 2 misses, and also include C.
Okay.
Or 5 misses rather.
You go into the right direction. There's actually a better trick, which is if you look at C, only have 2 hits, right? The only way that C can have 2 hits is like C 2 hits in terms of access latency means that everything that goes before C, which may be somewhere from here to here, only incurs 2 row hits. The first row hits already happen when channel 1 bank 0 is already open, has R7 open, so this one would definitely be a row hit. You have only 1 more row hit to I guess to satisfy this requirement over there, which means that if you, for example, if you make n's equal 2, in this case, well actually n equals anything greater than 4. In this case, you have more than 2 row hits in total. So you can eliminate anything that are 5 and beyond. So in this case, at least n is from 1 to 4. So if you work through C, you know that n is between 1 and 4. And then you just work through A and B with the same, I guess, with the same chain of thought. You look at B and say, oh, there's 3 hits over here. And also, if you combine both of them, you get that there are 12 requests, which is the total of this. So if the batch is less than 4, it means that if you work through B over here in channel 0, you should see something less than that many number of requests, right? Because B ends here, which means that you should have roughly less than 12 requests. So that requirement, that latency is being observed from channel 1. If you work through the B, the only way that B will see 3 hits and 9 misses. Let's work through this. What if n is 1? N is 1, you say 1 hit, and then you see another hit over here, because that's 2 hits, and then nothing else. So 1 is impossible. For 2, you see 1 hit over here, and over here still 1 hit. The open rows are 4. See 1 more hit over here. Open rows are 1, and then no hits, no hits, no hits, and then no hits. So I think with n equals 2, you can satisfy that requirement. And for 3 and 4, it's the same thing. You work through that, and you see it's 3 hits and 9 misses. So over here, you eliminate 1 from the potential candidate, right? If you work through A, in a similar manner, n equals 2 will get eliminated from this channel. So in the end, you see that n can either be 3 or 4. So that's the solution for this particular problem. And for the last problem is for a given access pattern, the same here. Choose the number of n that has a lower stall time than when you use FRCFS. And the stall time when you use FRCFS is 7 hit and 4 miss. So FRCFS, you see 7 hits and 4 misses. Any taker?
Can we see the question?
Oh, so what's the number of n such that the stall time for C is less than this?
Isn't it just anything? That's what it was with FRCS. Isn't it just anything less than 12?
You mean here?
Yeah. Because then
I believe if it's say for 11, for example, you have this whole group,
yeah.
and then it would cause extra misses because R4 over there.
But it's just asking for C, right?
It's asking for C, but
There would be one less hit or miss regardless. Yeah.
No, because you'll have more hits that happen after the request comes in. And that increases the stall time for C.
yeah.
But C is included in the first batch. But C is included in the first batch.
Yeah.
But it's change the pattern.
To 11, and you have a lot more requests after the C
Yeah.
requests that are in the same batch.
Yeah, but you you don't have to wait for the end of the batch to get the value.
No, but inside the batch, you're following a RFCFS.
So within the batch.
No matter what, you're removing one of the hits that would have happened before C, that would have been served before C.
Yeah, because C is the very last one.
Reducing hits.
And you make it any shorter than what?
Well, not exactly though, because the last one is what I can't read the wrong.
R4, it's a hit.
Right. So last one.
If you
is
use a
R.
full batch, it's going to be a hit in this scenario.
Yeah, I know what you're saying, but I worked it out and.
Yeah, but I think we worked it out.
When it's 11, it's actually equal to FRCFS because there's if it's
I
11, there's
think
a,
it costs
there's a miss in the middle.
extra miss in the middle.
There's a miss in the middle for R8, I think, on
Right.
the B, which would happen later.
Yeah.
Or R3, sorry.
So what he's saying is because that's R4 over here, and if the batch size is 12, this R4 would get, if it's 12, we would get service over here, right?
Yeah.
But because that one is not here when n is 11, when there'll be something causing a row miss over here.
Well, that doesn't make any sense. That can't cause a row miss. Like it's the same ordering. You're just removing
No, but
one hit.
if you work it out, it'll be equal. So it's equal to FRCFS. Yeah. You can work it out. If you want to work it out. Yeah.
Logically, that does not make sense then.
Okay, sure. Yeah, let's work it out. So open row is R7 to have one hit. Right, that's only one hit. The next one is R4. So you have one miss, one miss, one hit, one miss, two hits. One more miss, miss hit, two hit, one miss. So let's sum it up first. Now you have one miss, one miss. So that's done. This is already done. One more miss, one more miss. So we get 3 miss, 5 hit, and then R8 in the back would get service. So that's 3 miss plus 6 hit. And then CR10 is 1 extra miss, so you have 4 miss plus 6 hits. I think that's it. Okay. Yeah, I guess we did it wrong. Alright, so yeah, so it's actually anything less than 11.
Well, it can't be too small because then you start introducing
Misses.
when the hits become misses, and then you have like 4 misses before C, and it gets worse.
Is there a number?
You break even. And then I think it's I forget what it is. But I worked it out because
If you have one,
if you have class size
like
of
person one, it would be 1 hit and the rest are misses. Well, 2 hit over there, and the rest would be 1, 2 hit, and then miss, 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 miss. So that's 5 misses.
the first couple either are worse or like
But is this worse? You save 5 row hits, right? So that's what you compare it to, right? So you have 5 fewer row hits, so that's 5 times 15. That's 75 cycle, and then 1 extra miss over here. 5 miss compared to 4 miss, and that you save 30 cycle. So if you work out the number, actually it's 45 nanoseconds faster. Unless I'm wrong. Right, so this will be a hit. That's 1 hit. 1 hit, 1 miss. 1 hit, 2 miss. 2 hit, 2 miss. 2 hit, 3 miss. 2 hit, 4 miss. 2 hit, 5 misses. 2 hit, 5 misses. And if that's 15 for each of them, this would be 5 times 45 times 15. This would be 7 times 15, 4 times 45. So that,
It just needs to be less than 19 times 15.
yeah.
We just divide everything by 15 and make that easier.
Well, that works too. So it's 7 plus 12. So that's 19. This would be 15 plus 2, which is 17. So this is faster. And I believe the same goes for n equals 2. But let's see.
It needs to be large enough to exploit the locality of the 2A hardcores, basically.
I think you have
right,
to.
because you're excluding the one. Yeah.
Yeah. I don't even have to because this actually ends a lot faster. Right? So yeah. All right, thank you for catching the n equals to 11 one. Okay, the last question, extra credit, building multi-core processor.
Now, for this question, I said because we're working with floating point, the order of operations matters. Was that a valid assumption?
You assume that it can be well, you treat it as a valid assumption. I mean, does it matter? I don't think it matters for the answer.
Well, I mean, from a point of like, you could do some trickery, and I mean, so right now, I mean, you could obviously extract this into 12 separate threads.
Yes.
But in theory, you would be able to extract more threads worth of work out of that to get even more parallelism. But you can't do that because order of operations matters in floating point. That's the point that I'm trying to make.
I see. Yeah. So the
I don't think that's the bulk.
yeah.
Not in the first one, because in the first part you have infinitely many, you have magically fast DRAM.
But that's yeah.
A of I equals past.
And current. And
No,
the
but what I'm saying is, we have this past plus current thing. You can calculate the first n of them in serial.
No, but
But then you can calculate the other
No, so
n
to
of them.
calculate the 12th one, you need the 0th one to be complete.
Yes.
I understand what you're saying.
But what I'm saying is, if you do something tricky with the algorithm, at the algorithm level, you could start at the 5th one down and just make an assumption about the past value, and then do a correction at the end.
What you're talking about is value prediction.
yeah. That's value. That becomes like value prediction.
Value prediction.
I mean, then how do you get the last
How do you get the last iteration of the loop? Because it's some random value in the array.
Right. But I mean, so this is a recursive how function, right? Or not? I mean, it's not. But I mean, from an algorithmic perspective, right? You have everything is every value is defined in terms of the value before it.
Well, 12 values before it, but yeah.
Well,
Yeah,
yes,
12 value
I mean,
before
but
it.
let's okay. But you could. I mean, maybe I should actually just work out the math and show the equation that you would get if you were to separate this out. That would make it.
I mean, so
clearer.
basically what you're saying is, let's say I want to calculate A of 5. Then I'm making assumptions for A of 5 minus 12. Doesn't exist in this case.
But you don't have to make an assumption about it at all, is what I'm saying.
But you don't know what that value is.
Yeah, but what I'm saying is you can make progress that is
Which is
not
value
in this
prediction.
order, but you can make progress without knowing it and then fill in the value later.
So how would you make?
So what you're saying is, okay, looking at the algorithm, you have to have the past value to
Yeah.
0.37 to it. If there was some way to simplify this logic such that you only had constants and all you needed was that memory value and you could do something with that, that's different. We don't have a case like that.
I'll work it out and then I'll
Okay.
present that.
Yeah. Alright, so because this question you have to wait until the 12 one question?
Still do a faster speed up than 12 times though, because you can use 2 threads within each. So you split in you do 12 loop iterations at once. You throw 2 processors each loop iteration.
No, but the second 12 will have to be based on the earlier 12.
I get that, and I agree with you.
Yeah.
So what I'm saying is you only do 12 at a time,
Mm-hmm.
and you load past and current in different threads. You do.
You told me because that the last 3, which is multiply and add, can
So yeah. So you can only use the extra processor for 2 out of the 4 operations.
That requires storing faster current back in the memory that manage with it. Or else they
Well, not with Magic Premium.
Then you also have to synchronize your threads.
Yeah.
So like,
not with manage.
Not with Magic.
Okay.
DRM has nothing to do with that. That's between core communication.
Yeah.
That's a big difference.
Is that specified in there as taking extra time?
I mean, if you
If-
choose that you assume that between core communication doesn't take any time, then we can consider that. But without that, you can't assume it.
Yeah.
It's a good part.
So now you have what's magic is the DRAM and memory and caching. All right. So well, I guess you guys got that the part where the speed up is 12.
Yes. I figured out the algorithm.
Okay.
Can I write it on the board? Or?
But do you want just let him go?
Yeah. Let us go through this first. All right. So that's for the first part. The second part was the minimum number of cores you need. This should be pretty obvious, 12. And briefly describe how you design it.
Basically, each core would be assigned an I mod 12.
Yes.
And step by 12.
Right. For the second question, so what's the difference here? Now you.
You have serial memory access,
Mm-hmm.
so that part can't be parallelized, so you can't achieve the same speed up.
Right. So I guess for that part, is it a yes, is it a no? No, yeah, because what you just said, you have memory and you have to, the serial portion, right? Then let's go to the next part of the question. What's the minimum number of cores to get the speed up that maximum here? Yeah.
I said 12. I had great reason at the time.
Okay. 12.
I do that.
I guess you can get that maximum speed up with 12, but it's not minimum. So if you look at the program, which is where's my
Why
mouse?
is it 12? Because when you, it'll have, I think it will anyway, have good use of the cache. If you use 12, then each one will be able to get the maximum locality out of the cache as you load each block. Because it'll come back to the same processor every 12.
No, but even with caching, this is all streaming to memory. How can you cache things that you haven't seen before?
Because they're using the cache block.
Yeah.
So you're still going to have the memory delay
Yes.
in every cycle,
Yes.
but I still think that 12 is the amount that you need because the linear. If you do it the math with the linear portion and the parallel portion,
Mm-hmm.
I think 12 is the right amount. What I found.
But how is that the right amount? Okay, I'm curious. How can you get 12?
What do you think about it? I'll tell you after this.
Right.
What was supposedly the limit?
So you're saying is overlap the memory latencies with calculations instead of processing those?
So you can overlap, but in the end, every 3 iterations you have one serial accesses through DRAM. So out of that 12 iteration that you get earlier, now you pretty much get only a quarter of that. So in the end, you only need 3 cores to get the speed up of 3.
Actually, using more than 3 cores will lead to a slowdown. The main reason is because when you're using exactly 3 cores, each core is fully taking advantage of their own cache. So you have like exactly once and fetch once.
Yeah.
The problem is that if you have more than 3 cores, one of the cores have to
overlap in terms of cache lines, because the cache line holds exactly 4 elements. So that means the same cache line needs to get fetched twice, one for each core, and that actually creates a slowdown in the memory bottleneck.
Well, what I said was re-interleave the array so that the processor is working on like a consecutive stream of memory.
Interleave arrays for every.
Actually, consecutive elements.
Oh, but then the second thread needs to wait for the first thread to start finishing before it can use it. But the problem is that if the first thread then writes back to the memory its result, then the second thread needs to refetch the entire memory input.
One thread is just working on every 12 elements.
That's correct.
Yeah, you need the one earlier, the 12 earlier. The I minus 12.
A given thread works on every 12, but those are moved to all be consecutive memory.
Yes. Huh?
Could you repeat that?
Yeah.
So like each thread is working on like a stride of 12 elements.
Yes.
They're all offset by a different.
They're offset by
Oh, you mean like
the index.
Like the first case where you have the, say, core 0 works on element 0, 12.
Yeah. Like
The problem of that is, again, then the cores 1 and 0, well, cores 0, 1, 2, and 3 all need to refetch the same memory location.
Right, but I mean, change how the array is laid out in memory so that they're all working in different cache blocks.
I see.
That's like changing the function.
That's like changing. Yeah.
Can you scroll down to part B?
Yes. I guess before my laptop die. There you go.
I mean, you are changing the program in the first place.
Well, you're changing the way memory layout works. Then, for example, if you're going to, say, pre-process the memory so that the stride fits perfectly, that's actually just going to take you more time than just doing the work, all right?
Yeah. Oh. Okay. Right.
Right, but you could ask.
Someone has to do the work.
Sure.
Break down the rows.
So what we're actually calculating here is this A0 times 0.37 times 0.63 plus A12 times.
Can I borrow like some of the like just one? I just want to see the program.
Individual can scale by
My laptop died.
Oh, okay.
Yeah.
I also want to see the program.
Now I see. Yeah.
This is effectively what we're calculating, right? This equation.
Mm-hmm. I think so.
Yeah, I see where you're going with this. Now, we didn't want to change the algorithm itself. The question was intended so you can reschedule the way the work is done.
Yeah, like
to achieve the maximum speed.
how you balance the load and stuff like that.
Well,
Yeah.
right, but if you make this change, then if you have an infinitely parallel machine with magic DRAM, then you can do this in log n time.
Yes.
So,
that is true.
right.
So what you're saying is record.
So the point
Yeah.
that I'm
So
making
so
is
you're
if we
telling
say that
we
it's
can
floating
record the
point
program.
and we care about those least significant bits,
Okay, but
then
you
we
can't
can't
do this with
re-
a given code, is what I'm
Yeah. Otherwise, what's the point of
Why-
us
why-
giving
why
you
can't
guys
the
the
compiler
code?
be smart enough to do this?
That's
I mean, I'm
a
making
really
the
huge
assumption that we have a
assumption.
good compiler for our parallel architecture. That's a good assumption.
If you use a normal GCC compiler, GCC compiler is not going to do that. So I suggest you can try it.
It might for
Well,
all
okay,
four.
yeah, but that's because GCC is targeting an architecture that's not stupidly parallel.
Okay, again, that's an assumption that you're making. So
Yeah.
You specify that assumption specifically.
If you put it in your midterm.
Well, I did.
Okay.
I mean, I stated the assumption that we could not do this reordering. So.
Oh, you
that
could
should be
not
fine.
do. Yeah, then you're
We
fine.
can't do this reordering because it's floating point.
Yeah.
Right. I mean, if it were fixed.
Yes.
Fixed point, then you would be able to, but you can't.
If you actually assume that, yes.
Right.
Yeah.
But.
All right. So let's go back to the regarding consistency for loosely coupled mounted processor. Even with no cache coherent inside each of the machine, you have to ensure cache coherent in the higher level when you're running the like a high level the program that shares the data. Huh?
For loosely?
For loosely.
But don't they not share?
They're not sharing in the lower level, like in the actual physical cache that are on each of the processor.
But they're not sharing memory. If
They're not sharing their memory, but
That's still
So what is
defined
it?
as cache coherency, though. For example, that would be saying like the web page on my browser's cache is having cache coherency with what's on the server.
so
That doesn't really-
that depends on the definition of what it means as a cache, like software cache, hardware cache.
But in the scope of this class, the way we talked about it was just like, we have this memory thing and we want to make sure that the caches that are on different CPUs or whatever are referencing the same thing in this like grouped memory.
So I got what you're trying to say, and you can try arguing with owner on that, because just to be safe here. I mean, yeah,
It's only like 2 points, right? It's okay.
right. Well, maybe. I'll have to check the rubric. But yeah, that's that. Lab 7 is, well, I not optional, sadly. I wish. It'd be, huh?
Which day is Lab 7 due?
5/9, is it 5/9? Yeah, 5/9. Well, Friday, push by 1 week. Friday during the final week. We would love to push it maybe a little bit further, but like we have to grade them, we have to get the grade up, everything done. So, huh? You can come by my cubicle if you want to demo after the final.
I don't want to demo. I asked him.
Do we have
You don't have to, but feel free to if you want to demo.
Do we have demos today for
Lab 6, yeah, we have demos. You can just drop by one of our office hour. Yeah.
Has the reference simulator been released or the test input cases?
Not yet. The ref sim, I think Varun is still debugging that. Varun is making sure it's
Okay.
bug free.